Hello everybody, this is Jenness and welcome to our fourth video on spatial data types. In this section we're going to be discussing a variety of special cases of spatial data. And these are sometimes similar to vector and raster data, sometimes they're kind of a mix of the two, sometimes they're completely separate from raster and vector data. Now, we're not going to use most of these in this course, but it's good for you to see what's available in case you run into them in the future. Okay, the first of these special data types is just a layer. These are the things you see in ArcMap when you load data in. So it's important to understand that the layer is not the data. The layer is just a set of instructions on where to find the data and how to draw it. A lot of instructions on how to draw it. You can set transparency, symbology, you can set rules about which parts of the data to show. So understand that layers are, they're not the data, they're sort of like the window through which we interact with the data. You can save layer files to the hard drive. That would mean you would save these instructions on how to draw it. It creates a file called a star.lyr file. You can also save a layer package, which saves both the data and the symbology itself. Next up is tables. These can be attribute tables. They can be standalone tables that aren't directly connected to any spatial objects. One thing to know that when you want to open up a table, especially a standalone table that doesn't have a feature class or a raster associated with it, you need to have your table of contents sorting style shifted to this thing called list by source. If a table doesn't have a spatial object associated with it, it won't show up when your table is set up to do list by drawing order. So here, notice that we have the sort or the list by sort option selected, and this is what allows us to see the tables in the table of contents. If we change this drawing, the sorting option to list by drawing order, then since tables don't draw, they just don't show up in the list at all. Okay, so that was tables. Next up, web maps and web apps. These are data sets that you post online. You can do this a few ways. You can just post data online, but more often you will set up symbology about how you want to draw the data, how you want it symbolized, and you post that to the online server as well. And so then it becomes available to be added into these web apps and web maps. Here's an example of the museum fire from last year. This is from Mark Manon here at NAU. If you want to go look at this, if you go to the PowerPoint and click on that link there, you can go see it yourself. It's kind of fun. Here's another example, a story map that shows some of the species that reside around the Grand Canyon. This is a popular one these days. This is the COVID rates as of August 12th, 2020, and of course there's a lot more people sick now than there were a week ago. Okay, next up, KMLs and KMZs. These are popular things these days. These are a spatial data type that were invented by Google. KML stands for Keyhole Markup Language, and KMZ is just a zipped KML file. Now, KMLs, they don't really fall into the raster versus vector breakdown. They can contain both data types. They are native in Google, but a lot of other GIS systems have realized the utility of these data, and so now you can open KMLs and ArcMap, and I suspect QGIS as well. So yeah, they're pretty handy data types. They're a little weak on storing attribute data, but they do a decent job of showing data that is symbolized. Yeah, and by the way, KMLs, they come symbolized. The data and symbology are all part of the file, so it's not something you can change very easily. Okay, next up, annotation. This is closely related to labels. On any feature class, you can set up labels and label your counties or your whatever your sites are. So the labels are kind of dynamic in ArcMap. If you change the scale, then the labels will move themselves around to arrange themselves appropriately. Annotation is sort of like taking a layer and locking it down to the ground. So they become spatial objects themselves. They're not movable, but as such, you can have a neat effect with them. So you can set up your labels, make them look nice, nail them down into annotations, and then you can rotate your map, and then these annotation labels will rotate along with the map. They become part of the map. If they're just normal labels, then you can rotate the map and the labels will still be all horizontal. Another effect is as you zoom into them, the labels become larger, and that's not what you usually see with annotation. Okay, networks. There's a few types of network data sets in the GIS world. First up we're going to look at is geometric networks. They're vector data sets that just incorporate connectivity. If any of you are familiar with graph theory has edges and nodes. Geometric networks take advantage of this model. You can model stream connectivity. You can model stream is a real good example. The thing about them is that they assume that there is no free will. There are rules about the network that tell exactly how objects will move as they traverse that network. So this is why stream connectivity is a good example. Water's always going to flow the same way, right? It flows downhill. So a geometric network is appropriate for modeling stream connectivity. You're never going to have water flow backwards along that unless you have an earthquake or something. So examples are utility networks, electrical and sewer systems, river networks, and geometric networks are stored in featured data sets. You remember the three broad categories, the three most common types of vector data sets are feature class, feature data set, and TIN. Well, featured data sets are where you store your geometric network. Now, interestingly, ArcGIS Pro is getting rid of geometric networks. They dropped them entirely when they created ArcGIS Pro, but so many people were upset they're trying to bring them back in the version of these new things called utility and trace networks. So they were gone, now they're starting to come back in these new flavors. Here's a geometric network as visualized in ArcMap. Remember they have nodes and edges. That means they have points and polylines that connect them up. So this geometric network shows you the data that is necessary to describe a water distribution network in a city. All right, so network data sets, I mentioned there are two of them. We've been discussing geometric networks. Well, next up is something called a network data set. And this is similar to geometric networks, but they are specifically designed for the network analyst extension. The neat factor about them is that you have free will and movement. The network is there, but you can set up any rule you want about how an object traverses the network. So it's useful for finding the shortest path between points on a road network, for example. Shortest route from the School of Forestry to Beaver Street Brewery. Well, there's going to take advantage of a bunch of streets. A shortest path from another location might use those same streets, but could go a different direction on those streets. So the fact that you can have different directions, in general, lots of street characteristics. This is what the network data set is useful for. You can incorporate one-way streets. You can incorporate streets that cross each other but don't actually intersect, such as an overpass. You can set up rules along the street that say you can't turn particular directions, or maybe you can turn different directions. And again, these are stored in featured data sets. So featured data sets, remember, a featured data set is what you use for describing a more complex system, something you can't describe with a single feature class. Well, these network data sets are good examples of these more complex systems. Now, network data sets are designed for the network analyst, and so here's some examples of things you can do with this. Network analyst is pretty cool, by the way, and if you would like to know more about it, I can get you a license to take the the online virtual campus course that Esri offers. It's a short little course, and they describe a lot of the cool things you can do with Network Analyst. In this example on the left, we see how you can set up a bunch of potential bases. Maybe you want to set up a bunch of stores, and you want to find, you have potential store locations, you have a bunch of customer locations, and you want to know what customers would be allocated to each store based on the shortest driving path. Well, Network Analyst will do that. And of course, Network Analyst will determine the best route, the shortest route from one place to another, as you see on the right. Now, it does something else that's pretty cool and is surprisingly powerful. You can set up a bunch of locations and find the best route to connect all of those locations. So a delivery person can find the best route to go to 20 or 30 drop-off points. The reason this is cool is that this is actually an example of what they call the traveling salesman problem, a famously impossible problem to solve. So it doesn't sound like it should be impossible. If you only have 3 or 4 locations, it seems like it should be doable to find the shortest route that connects them all. But it turns out that once you get up to 20 or 30 locations, you get so many possible permutations that it becomes impossible for even the fastest computer in the world to solve. Get a few hundred locations, then you need a computer operating for the length of the life of the universe to analyze it. Surprisingly complicated. So the fact that Network Analyst will do it is kind of a shock. And so the secret is that it doesn't give you the best route. It doesn't guarantee the single best route to connect all these drop-off locations. But it will come close. And the fact that if you're willing to accept close, then it becomes doable. So it's pretty cool. All right, so those are network data sets. Moving on, we talk about multi-dimensional data sets. In the GIS world, you'll see these referred to as several things. There's this NetCDF format, Network Common Data Form. This is the most common, and I got another slide of that in a second. But there's also data sets in format of HDF, of cloud, raster formats. And now Esri's going on and on about image cubes. They're all basically the same thing. They are often used for data-intensive scientific applications like 3D climate modeling or ocean current. They are also difficult to work with, especially in ArcMap. ArcGIS Pro and QGIS are both much better designed to handle these multidimensional data sets than ArcMap. But ArcMap still, if I have to deal with NetCDF data, I'd probably go with Pro or QGIS instead. Most of these are sort of like rasters. Not all of them. Some of these types of data sets incorporate both raster and vector data. Some of them just incorporate tables. But the cool thing is that they can do multi-dimensions. So if we look here on the left, we have a typical two-dimensional data set. This is what you see in a normal raster. On the right, we see that we're adding a third dimension, and so we can have latitude and longitude incorporated here, but we can also have altitude or elevation. Now, you could sort of replicate this just by taking advantage of the multi-band nature of rasters, so you could have a different band for each altitude. The multi-dimension data sets kind of take this a step farther, though. But anyway, in these two examples, I'm showing you how 2 dimensions can be expanded to 3 dimensions, becomes a true multidimensional data set. And these data sets can take that even further. You can replicate this for every day of the year, for example, so you can add date as a 4th dimension. You can add any number of dimensions to it. That's the neat thing about them. You can have as many dimensions as you want. Here's an example of a NetCDF. This is a common format, the Network Common Data Form. And I tell you, I've had endless grief making this work in ArcMap. It really doesn't work well. But it is interesting that the only times I've ever dealt with these raster-type data sets that didn't have square cells, it was in NetCDF. So these network data sets can have pixels that are not square. They can be rectangular. Neat thing about NetCDF, though, is that the data format itself has functions embedded in it that allow you to query it in cool ways. So when you get a network data set, you don't have to deal with the entire world like I'm showing you in this picture. You could tell it just to show you a particular latitude and longitude range, and those are two of the dimensions. You can tell it a range of values within any of the dimensions that are in there. So if you had time or any other dimension, you could specify a range of values that you wanted to extract. Now, like I said, I hate using this in ArcMap. It's just a pain. Some of the best tools I found to work with NetCDF data are actually in Linux, and people who love this data set are often Linux fans as well. So learn Linux if you want to go further in this. Next up are terrains, and terrains are tin-based vector surface data sets. Tin, remember, is triangulated irregular network. So they're tin-based data sets that are optimized for quick analysis, editing, and viewing. They're similar to tins in that they treat the landscape as a continuous surface of connected triangles, but the data set's not actually stored in tin format. The triangles are created on the fly as you view it. So terrains take advantage of pyramids, and we're going to discuss pyramids again in a second. But this allows them to be drawn at a coarser resolution when you're viewed at smaller scales. So terrains can also incorporate information from points, lines, and polygons. But notice that we're looking at this in three different scales. When we're at 1 to 170,000, it looks one way. As you zoom in, it redraws itself at a higher resolution, and you keep zooming in until it draws itself at the maximum resolution. And tins are stored in feature data sets, so you can't store a tin next to a shapefile. It has to be stored in a geodatabase in a feature data set. Next up is LiDAR, and this is one of the more exciting new things that's being developed in GIS. LiDAR is much like radar, but it uses lasers instead of radar waves and produces this point cloud of three-dimensional points, usually huge numbers of points. The locations of the points are determined by the time it takes to get a return signal from the laser, so it's calculated from the speed of light. And there's some interesting new research going on where people are using different wavelengths of a laser beam. Now remember that the landscape reflects differently at different frequencies, different wavelengths in the spectrum. Well, if you can use a laser that shoots out a beam at different frequencies, then you get different qualities of reflectance, and you may be able to use that quality to calculate vegetation health, similar the way you can with satellite and aerial imagery. Parcel fabrics are a special type of feature data set that are designed to map property boundaries, and they often include polygons that represent land ownership parcels, polylines that represent various edges and survey measurement regions, and points that represent various types of control points. So you see these a lot in county government and city government, where they're mapping out the ownership of the community. A topology is a special type of spatial data structure. It tells related vector data sets how they are spatially related to each other. Topology is not typically a data set itself. So if a topology has been defined between two data sets, then if you edit one data set or feature, then you can cause corresponding edits to happen automatically in another data set or feature. So in this example, we have two stands that are mapped out. Well, we realize that the boundary that separates the two is mapped incorrectly and we want to move it. We would like to edit that boundary and have both polygons be adjusted simultaneously. And in order to do this, you need to define a topology between these two polygons. So topologies can also be used to ensure that the edited data is valid, like if a polygon, you draw it out, but maybe you have a little dangling line that sticks out. Well, that's not legal in a polygon. So generating a topology can help you identify where these errors have happened. Now, some data sets actually have a topology that's built right into them. Coverages and tins, for example, have the topology embedded into the data. But most data sets don't have any internal topology defined. And like shapefiles have no internal topology. A shapefile will just show two stand polygons next to each other. And there's nothing in the data set that tells it that they share a common boundary. So when you do editing, ArcGIS just creates this temporary topology in memory. Now, ArcGIS does allow you to define complex topological relationships between datasets, and you can add them to feature datasets to help find problems in the data like I described. Now, these examples include polygons or polylines that almost but don't quite connect, like you're mapping out a trail system through the forest and you're digitizing individual segments. Well, you would like those segments to touch each other, right? Because the trail itself is continuous. Topology can help you identify those places where the polylines don't connect. And polygon segments that overshoot or make little dangling edges. This illustration shows how I've used topologies in the past to identify just those types of errors I've been describing. In this case, we wanted to map a network of trails and roads across the Grand Canyon region. And so I digitized a bunch of lines. Well, remember the network datasets we discussed earlier? They can help you define the shortest path between 2 points. Well, that ability to do that assumes that all those network polylines are connected, right? If there's some little gap between polylines, then the networking algorithm can't jump that gap. So that gap may be a fraction of a millimeter based on how you're digitizing. And so you want to identify all those places where there's tiny little gaps, and this topology function is the way to do it. Here I find all these places where the polylines don't quite map up, don't quite connect. This term topology is actually an interesting choice. It comes from the mathematical definition of topology, which some of you may recognize if you're into some of these more esoteric and advanced fields of mathematics. It's all about how the surface of an object connects with itself. So in spatial analysis, we understand it in terms of how points, polylines, and polygons connect with each other. But mathematicians love to think about topology on weird surfaces like donuts, which have holes in it. Maybe Mobius strips, you're familiar with those from elementary school, where they only have one single side and a single edge. Or even better, you can map over the surface of a rope that's tied in a knot. Anyway, that's enough of special cases of spatial data types for now. So in the next video, we'll discuss several more special cases. Then we'll wrap up with metadata and talk about some basic data management strategies. Thanks, everybody.